How equalizer works in frequency domain is also very interesting. Recall that for a low data rate scenario, our signal bandwidth is very small. Intuitively, we know that a small bandwidth implies our data rate is slow. When we increase the data rate, we increase our signal bandwidth, which implies that the same channel, which was frequency flat, has now become frequency selective, which implies that it affects some parts of the signal bandwidth differently than the others. Expansion of signal bandwidth has resulted in a frequency selective channel. The main problem arises because equalizing a wide spectrum is computationally very complex. To solve this problem, we have a view of subcarriers in frequency domain. Recall from lecture 1 that a complex sinusoid or a subcarrier is given by an impulse in frequency domain. When we limit this subcarrier in time domain equal to the block length, this is equivalent to multiplying it with the rectangular signal in time domain. The rectangular signal has a frequency response which is a sinc signal, and multiplication in time is convolution in frequency. From their multiplication we get a subcarrier which is time limited, and from their convolution we know that the convolution of a signal with an impulse is a signal itself at the position of the impulse. So the subcarrier comes at this location. Here is the complete show. This is frequency domain, and the peak of the subcarrier lies on a point where the contributions from all the other subcarriers passes from 0. This is a beautiful analogy with time domain pulse shaping we discussed in lecture number 3, where we had these independent pulses carrying the modulated data, and we said that the Nyquist-Noisy criterion implies that the peak of the pulse should lie at a point where the contribution from all the other pulses are 0. And this is a modulated case where these subcarriers are modulated with +1s or -1s. The important step is why equalization becomes simpler and makes our high-speed wireless communication possible. In frequency domain, and these are the same subcarriers but in dB scale, this is the wireless channel we have seen earlier. Clearly note that each subcarrier is affected by its own channel. We say that the subcarriers have sampled the channel at n different locations in frequency domain. And for each of these subcarriers, we can write Z equals data symbol multiplied by the channel value. From here, we can see that the equalization becomes simpler because each AK can be written as Z over H. Now, if there are n subcarriers, we have an equalizer that consists of n deviants, and that's it. Regardless of the channel length and regardless of the equalizer complexity in time domain, this equalizer in frequency domain in an OFDM system just implements n deviant, one for each subcarrier. This is an intuitive view of how the value of each channel gain results. This is because of the addition of the sinusoids or subcarriers of the same frequency adding in a vector sum. If you do not understand this concept, you are free to ignore it. This figure is drawn just to give you an intuitive idea of how the channel gain is made at each subcarrier. And the reason is that we have a vector sum of different subcarriers, each has a different amplitude and a different phase. They are all independent to each other. The frequency domain perspective of OFDM reminds us of the sliced bread. Before 1928, it was very difficult to process a bread. We have to cut individual pieces to put cheese, jam, or butter on each piece. But OFDM slices the spectrum in the same way as a bread is sliced for easier handling. And this is one of the main reasons for the attraction of OFDM systems for high rate wireless communication systems. The summary in frequency domain is that OFDM segments the available bandwidth of a frequency selective channel into a set of parallel frequency flat channels. This is what you have seen here. A frequency selective channel has been broken down into a set of parallel frequency flat channels.